Good morning, everybody. Okay, welcome to Papa Lim Physics Classroom. Okay, today paper we'll be going through is Bukit Panjang Government High School. It's one of good paper that I got from one of my students. Okay, today we'll go through that particular paper. If you have not done the paper or if you need the paper, I have shared in my Google Drive, which is down below at the link below there. Okay, feel free to go and download. Okay, and go and try out yourself. Okay, if you have done it, okay, and we will go through and you have some questions. Okay, this is the time whereby you look at the questions that you need and to see what are the mistakes that you make, okay, that you can actually improve on, or what are the gaps in your learning that you want to bridge. Now, without delaying, okay, this is the paper we are going through. If you have done it, okay, I will flash the answer for the MCQ. Okay, you might want to pause the video here. Then after to check your answers to see which are the questions that you have mistakes. Then after that, zoom in directly on that particular question. Okay. Yeah. This paper is quite interesting actually. Now, for the first MCQ question, okay, the approximate diameter of the atoms. The only way to know about this is to read up on your chemistry book or your, I would say chemistry book. Chemistry book will have a lot. Okay, so you just need to take note of the possible dimension. Okay, the rationale of this question is to actually let students know a gauge of how big your prefixes is. Okay, like example, giga, how big is giga, nano, how big is nano, all these things. Okay, so the gauge of your prefixes to see what is the understanding of your sizes. Now, question 2. Okay, if you look at question 2, now question 2 is a very classic question, but you just phrase it in a, I would say in a quite a new way. Okay, whereby it give you like 6 and 8 newtons are being actually applied onto a particular object, and the resultant force is R. Okay, and the question asks like, what if the angle can change? Okay, what are the values that R can not take? Okay, this type of question, usually the approach is the same. What I actually encourage students to do is actually to find the maximum value, okay, of your resultant force, and actually to find the minimum value of your resultant force. What I'm trying to do is we want to find the range of forces, the range of FR that could occur. Okay, so if by knowing the range, the maximum and minimum, okay, by knowing the maximum and minimum, I will be able to know the range of FR whereby force R, the resultant force, is possible. If I know the range that is FR is possible, then I will actually indirectly know the range whereby, or the values of R whereby resultant force is not possible. So for example, for maximum FR is whereby the two forces are in the same direction. So my 6 Newton and 8 Newtons are in the same direction. So the resultant force of this will be 14 Newton. So this is the maximum number I can have. For minimum R, okay, minimum FR is whereby 6 Newton and 8 Newton are in opposite direction. Okay, and the resultant force will be 2 Newton on the right. So the range of value that will actually take place will be ranging from 2 Newton to 14 Newton. So any value in between 2 Newton to 14 Newton is possible. Okay, just that the angle will be different. Okay, so 2 and to 14 is possible. So this will leave me the answer to choose D. Okay, whereby 16, which is out of the range, is not possible. Okay, so this type of question usually is quite, I would say it's quite a common one, and the approach is usually almost identical. Whereby I need the students to actually find the range of the possible values of FR. And how do I find the possible range of values? Okay, by looking at the maximum number and the minimum value. Okay. Question 3, sorry, is a classic example of Newton's law, F net equal to ma. Okay. The mass is given. Double check, make sure it's in kg. Mass is always in kg. Okay, and there's two forces that is applied on the particular car: the 3,600, which is the engine force, and the 2,000 Newton, which is what, based on the question, is the resistive force. So the net force will be F net. Okay, will be the 3,006 minus 200. Sorry, not 200. 3,006 minus 2,000. Mass is 800 divided by times A. Okay, so if you do algebra, you'll be able to find the acceleration of the car here to be 4.5 meter per second square. The key thing that we have to always remember is that F net refer to the net force on the object. All the forces in the same axis has to be accounted for. So that's why both forces must be in the equation. Now for question 4 is a standard example of like mass balance and spring balance. Now, first thing first is students, we have to be sure like you know spring balance, what does it balance, what does it measure, beam balance, what does it measure? Okay, a classic example that we look at is whereby beam balance is comparing both sides. Okay, whereby the stone is being compared to what we call a standard mass. Okay. So the principle that we are using here is actually we use the principle of moments, okay, whereby we want to balance each other. But ultimately, what we are looking at is for beam balance, we are measuring the mass of the object. Okay, so beam balance is for measuring mass. So spring balance, okay, straightforward, is the pull of the gravitational field on the particular object. So basically, spring balance measure the weight of the object. Okay. So once you are clear with like beam balance measure mass, spring balance measure weight, you will be able to identify that for beam balance, because I measure mass, okay, regardless of location, whether it's moon or earth, mass will always remain the same. Okay, mass is the amount of matter in the body. So the amount of matter remain the same, regardless of location. So mass will be the same. And similarly, weight, we all know the formula, weight equal to mg. Okay, weight depends on two factors. One is the mass. Okay, the other one is the gravitational field strength. Okay, on moon, and on Earth, the gravitational field strength will be different. So definitely, the weight of the object will be different. So that's why the answer here will be B. Okay, so the key things that we like to take note is not just the differences between mass and weight. It's more importantly is the instruments that is needed. Okay, so beam balance is for measuring mass. Spring balance is to measure weight. Okay, this is one of the segment that we tend to forget, not commonly. Okay, but it's in the syllabus, so it's good to take note. Okay, question 5. Question 5 here, what we are looking at is the density of the object. Density, okay, will be the mass. Okay, the formula mass per unit volume. So what I need is actually I need the mass of the object, mass of X divided by the volume of X. I will definitely have the density of X. Okay, so what I need is, okay, find the mass of volume of mass and X and volume of X. Okay, so let's look at the math. Okay, the first statement mentioned is the mass when it's filled with water is 200 gram. So knowing that the bottle is 80 gram. Okay, so if given these two numbers, I will be able to know that the mass of water, okay, is actually 200 minus 80, which will give me 120 gram. Okay, so that's the mass of the water. Now, with the mass of water and with the density of the liquid, okay, of water to be exact, okay, which is 1 gram per cm cube, I will actually know that the volume of your water is actually 120 centimeter cube. Okay, and why is this important? Because once I know the volume of the water, which is the volume of the container, which is volume of the bottle, they are the same value. Okay, and with the volume of water known, I will be able to identify the volume of X in the liquid. Okay, because after that, the bottle is actually filled with X again. Okay, so what happened now is I actually know the volume of X is actually volume of H2O, which gives me 120 centimeter cube. Okay, so volume of X is known already. So now what do I do is I proceed to the next part whereby I need the mass of X. Okay, so if I know the bottle is 80 gram, okay, and I know that with X and the bottle is 180 gram, okay, I will be able to identify the mass of X. Okay, it will be 180 minus 80 gram, which will give me 100 gram. So for mass of X is 100 gram, volume of X is 100 gram. So actually I have all the values that I need. So what do is I will just do a simple substitution. Volume of substitute into the denominator. X, I will substitute into the numerator. Okay, so it'll be 100 divided by 120. So if you look at the calculations, you will find that the answer will be B, 0.83. Okay, so this is what we mean by using math to solve the question. Okay, now although it's an MCQ question, it doesn't mean that the math involved is like a one step working. Okay, if you look at this particular question, you need to do like a few steps. Okay, so time needed for this particular question is actually quite I would say quite long. Okay, so students, you need to be sure of what you're doing. Okay, and you have to work on it fast. Okay, now the question 6. Okay, pressure. Okay, pressure formula we have to take note is force per unit area, which is the perpendicular contact area. The only thing we have to take note here is the pressure here is 2 kilopascal. 2 kilopascal in SI unit, it will be 2000 pascal. Okay, so the pressure here will be 2000 pascal. Okay, the force that we are looking at is 400 Newton, and I will have the area, okay, using the math, using the algebra. Okay, so from here, I will be able to work out the mass to be 0.2, okay, meter square. Okay, remember to change the prefixes kilo to pascal, okay, before you can get the answer. Okay, if not, their value will be totally different. Okay, so take note of the prefixes. Formula F over A is quite a standard formula, so take note of this. Okay, now so this question, what I suggest to students is like for question 5 you need more time. For question 6 you actually need like less than 1 minute. So solve question 6 as fast as possible and use the remaining time for question 5. Okay, if not you will be running out of time. Because for science paper, okay, for science paper, you need like for paper 1, you have 40 questions in 1 hour. So literally it's like one question is like 1 minute. You need to spend like 1 minute or less. Now, question 7. Question 7 is a good one. Okay, question 7 is a good question. Now, for question 7 here is the questions require you to apply the smallest force. Okay, smallest force to push over the step, which is, I would say the steps, the pivot is at the step here. So this is where the pivot is. So if you look at pivot and you look at the forces, you will bring us to one topic known as moment, force times perpendicular distance. Now to overcome the steps using the smallest force. So which means this force must be the smallest. To overcome it, meaning I will require force to be smallest, aka I will also need the perpendicular distance to be as large as possible. Okay, probably largest. If I have the largest perpendicular distance, I will definitely need to apply, let's say, a small force on itself. Okay, why? Because to overcome that steps, okay, the moment here is a certain value. It needs to be a minimum value. So I would say that the minimum value here is always remain constant. Okay, so the minimum value is always constant. So for me to apply the smallest force, but yet I need that magnitude of moments, I will definitely need my perpendicular distance to be the largest. So I will need to top it up with a large perpendicular distance. So let's look at the perpendicular distance. Okay, for D, if my perpendicular distance is here, same thing. If you look at the ruler, okay, the pivot is here. Okay, so the perpendicular distance is between these two lines, these two red color line. So the perpendicular distance for D will be actually here. Okay, so this will be the perpendicular distance for D, will be this particular length here. Okay, I would say like maybe like 3/4 or I'll say 3/4 of a circle. Okay, so this would be this particular length. Okay, so if you look at different if you look at different forces at different option A, B, C, D, you'll find that the perpendicular distance will change. So your choice of perpendicular distance, you have to literally look at all the force choices, and you'll find that the one with the highest perpendicular distance will actually be C. Okay, why do I want to put C? Okay, so let's say this is the C, the line of action of C. So what do I do? Find perpendicular distance, copy and paste this line, I bring it to the pivot. Okay, I bring it to the pivot. Okay, so now you have two parallel line. Okay, let's make it the same color. So I have two parallel lines. So what I do is now I will put ruler between them. I will find the shortest distance between them. Okay, so the red color line, it will be the shortest distance between them, which is the perpendicular distance I need for C. Okay, and the perpendicular distance for C, if you look at all the options, you will find the perpendicular distance for C will actually be the largest. This will be the largest. Okay, and as such, okay, I will definitely have the smallest force applied. So that's why if I want to push the ball, okay, across the steps using the smallest force, I will definitely need to have the largest perpendicular distance, which is why I will apply it at my force to be at C. Okay, so look at the technique of finding perpendicular distance. Okay, same thing. If you forgot about the technique of using perpendicular distance, I have done it in my chapter 5 topic. Okay, the link or the location of the file is at the bottom below on the screen. Okay, you can take a look at that particular video. Okay, if not, I also have link. I have left the link in the description panel below, so you can actually click on the link and just go straight to the video itself. Okay. Now for question 8. Okay. Question 8, molecules when the temperature increases at constant volume. Okay, so the temperature increases. Okay, what happened to the molecule? Okay, so the moment when the temperature increases, okay, temperature increases, the two outcome, I would say the most straightforward outcome is the kinetic energy of the molecules will increase. And because of that, the velocity of the molecule will also increase. Okay, they'll be moving faster and faster and faster. Okay, because they have higher kinetic energy. Okay, so once you know this is the first direct impact of increasing in temperature. So straight away you look at the options. Do you have one option that is like it fits perfectly? Yes, you have, which is option B. Okay, increase is greater average speed. Okay, so the moment you see this, straight away you choose the answer already. Because when we talk about kinetic energy, when we talk about internal energy of the particles, okay, one of the internal energy is kinetic energy. And kinetic energy of the particle, okay, it is tagged directly to the temperature and it's pegged directly to the velocity of the gas molecule, and both of them are proportional. Okay, the higher the temperature, the higher the velocity. Now, for question 9 is a classic example of like a mode of transfer, and particularly what we are looking at here is there are a few possible questions that they might be looking at. For example, polyestyrene. Okay, polyestyrene is the medium. Okay, it's the material of the substances. The question could be talking about conduction. Okay, because material usually evolve around conduction. Aluminum foil here, I would say very commonly aluminum foil, we look at the shiny surface, reflective surface, very shiny surface and the dull surface of the foil. So usually the moment I see aluminum foil, maybe I will peg directly to radiation. Okay, so these are what possible way the question could ask. Okay, and true enough, okay, so once you are ready, okay, once you analyze the picture, okay, maybe you can look at the question to see what they are asking for. Okay, which of the statement correctly explain why the board provide a good heat insulation? Okay, heat insulations, okay. Look at all the options. All the options revolve around polystyrene, 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 polystyrene. So straight away, like I mentioned before, polystyrene is the material. It actually has direct impact on conduction. So straight away, I will know emitter, reflector will be out of the question straight away. All my choices straight away. Okay. And in fact, polyestyrene, you know, is a material. And what so fantastic about this material is that they have small pockets of air inside the particular objects in this particular material, and it's actually a bad conductor. Okay, because of material. So this is what we call a bad conductor. And the one with a bad conductor, only option C. Okay, so C will be the option that I need. Okay, look at how I analyze the questions to anticipate what are the possible ways or what are the possible angles that the question could ask after I tackle it accordingly. Okay, so if I know it's a polyestyrene, it could be about conduction. If the question is asking about aluminum foil, it could be looking at radiation aspect. Okay, so look at the question, analyze it, okay, accordingly. Cooling curve. Okay, so cooling curve, take notes. Cooling curve, you need to pay attention, is the energy that is given in the different stages. Okay, particularly the four constant stages here. Okay, the four constant stages that we are looking at. So for this question, right, if you look at the pattern is more like cooling curve. Okay, so primarily there's a 4 stages. Okay, so will be the cooling stage. Okay, we're at the cooling stage. Okay, so this particular will be the gas cooling down. Okay, and then this cooling stage will be the liquid cooling down. Okay, in between the horizontal stages will be the condensation and the freezing stages. Okay, so these are the stages that you need to take note of it, and the freezing. Okay, particularly all these stages, okay, involve the internal kinetic energy and the internal potential energy of the substances itself, okay, of the molecules. Okay, so you need to know what you are looking at. So especially example for cooling, okay, we know that if it's cooling down, the energy will be given out, all this energy will be given out to the environment at different stages. Okay, at different stages, EK will be given out, at different stages, EP will be giving out. Okay, so it depends on what you are, what stages you are looking at. Okay, so you need to know what are the energy involved at the cooling, okay, at the condensations, cooling, and freezing stage, what energy. So you need to take note of it. Okay, so for particular question 10, okay, the answer that you're looking for is actually D, whereby 2 to 6 minutes. Okay, you look at 2 to 6 minutes. Okay, at 2 to 6 minutes, we are looking at these particular stages. Okay, 2 to 6 minutes. Okay, we are looking at condensation, and we're looking at condensations here. The energy involved is actually EP will be decreasing. Okay, because there's a change in state, and EK will be actually remaining constant. Okay, so you need to know what are the energy changes at each stage. So that's very, very important. Okay, so that's why if you know the energy at each stage, you will be able to identify the energy change, and you will be identify the correct answer that you're looking at. Okay, so for example, if I'm looking at the red color one at either of these 2 stages whereby you're cooling down, the energy that is changing, it will be the EK, but the EP will actually remain constant. Okay, so you need to know what are the energy changes at each stage. Okay, so take note of it, refer to your notes. Okay, if you need, okay, you can refer to my video on thermal property, whereby I talk in details on the keywords, okay, and of the energy change. Okay, question 11. Question 11 involves a bit of math. Okay, so but the main concept that we're looking at is angle of reflection, angle I equal to angle R. Okay, angle incident equal to angle reflection, which is law of reflection. Okay, so for example, if I look at the ray diagram itself, okay, the incident ray is 60 degrees, the reflected ray will be here. It will also be 60 degrees here. Okay, so based on law of reflection, the angle I, angle R will be the same. And because we know this is 60 degrees and we know that this is the normal, this line is the normal, this angle here will be 30 degrees. Okay, and if I know this is 30 degrees and I know angle in a triangle is 60 degrees, sorry, 180 degrees. So I would know that, okay, the angle of reflection, the angle of incident, the angle at, I would say, at the other mirror Y. Okay, 60 plus 90, this will be 90 degrees. So the remaining angle here, this angle, the remaining angle here will be 90 degrees. Because if you look at it as a triangle, all the 3 angles in the triangle will add up to be 180. Okay, so the angle that hit the ray will hit mirror Y at 90 degrees. Okay, now at 90 degrees is what we known as perpendicular to the mirror, or sometimes we known as angle I will actually be 0 degree. Okay, remember when you look at angles of reflection, angle of incident is always measured from where? From the normal to the ray itself. Okay, so take note of the way I measure. Okay, so if I know that the angle Y here will be, if I know the angle of incident is 0 degree, the reflected angle will also be 0 degree, because the angle of law of reflection say that the 2 angles are actually identical. So the answer will be 0 degree. Okay, so this is how I look at the angle here. Okay, so here involve a bit of math. Okay, and of course the use of law of reflection. 12, okay, electromagnetic spectrum, okay, which of the statements is false? Okay, so please take note of the property. I will not dwell too much on question 12. Okay, is the property in the EM spectrum. So most of the books and most of the notes actually will cover quite a lot on this. Okay, which of the following is not the application of X-ray? Okay, now X-ray, the main users for X-ray will actually to look at detect fracture. Okay, to look at what we have is this see-through effect. Okay, whereby I can look at what is beneath the skin layer. And same thing, beneath the layer, okay, I can also use it to detect flaws in the welding. Maybe got air pocket inside. It's like an X-ray vision. I can actually see what is below or beneath the layers. Same thing if not commonly used, but it can be done also. X-ray can also be used to sterilize equipment because it has a high energy wave. I can actually use to kill germs. Okay, that's on the medical equipment itself. Okay, although it's not common, but it still does. Okay, so one of the things that is not an application is component application is definitely detecting of forgery. Detecting of forgery, usually we look at is UV ray, okay, ultraviolet ray, the bluish purplish ray. Okay, so that is one of the application that's not using X-ray. So that's why the answer is D. Okay, so for here I will say take note of sterilizing equipment. Okay, it's not commonly used in X-ray, but it can be used. Okay, so take note of it. Pitch and loudness. Okay, pitch and loudness, I think we have mentioned it quite often enough. Okay, when we talk about loudness, okay, we talk about amplitude. When we talk about pitch, we definitely talk about frequency. Okay, these are the two things that we look at. Okay, and together they combine. We will have one formula that is quite commonly, which is V equal F lambda. Okay, for the speed of sound, remember speed of sound in the same medium, the sound is always, or the speed is always constant. Okay, it's always a constant number in the same medium. Okay, in the same medium. So these are the things that we want to take note of it. Okay, so let's take a look. If I have a amplitude, a loud note, okay, a loud note definitely will be a loud amplitude, or a high amplitude will be a large amplitude. Low pitch, if it's low pitch, frequency will be low. Okay, if the frequency is low, if my frequency is low, okay, and I have to achieve the same speed, okay, in the air. I will achieve the same speed in the air. The only possible thing for me to do that is whereby my wavelength, okay, has to be large. Okay, my wavelength, if this is small, this is low. Okay, to achieve the same constant, the speed, my wavelength has to be large, or sometimes what we call long. Okay, so that's why, so that I can achieve the same speed in the particular medium. Okay, so that's why the answer here will be A. Okay, wavelength long, amplitude will be large. Okay, so take note of this. Now for 15, okay, echo. Okay, echo, remember echo, when we talk about echo, we talk about bouncing to and fro. So let's say if I'm the person here, the moment we mention echo, okay, the moment we look at echo, it's always about 2 times the distance, meaning the sound will be traveling, example, from the person, from the source to the wall and back to the source again. So there will be actually 2 length, okay, 2 times the length that is, or 2 times the distance involved. Okay, so 0.8 second later, 0.8 second later here is for where? To and fro, okay, from the obstacle to the object itself. So here we look at a bat. Okay, so maybe I don't use the person here. So let's say I use the bat. Oh man, I can't draw a bat. Let's draw a bat. Okay, is this a bat? Okay, I'll say this is a bat. Okay, so this is a bat. So I send an echo, I detect it 0.8 second later. So it's 2 trip. Okay, so it'll be 0.8 second later. Okay, meaning for the sound to go to the obstacle, it will take 0.4 second. Okay, come back, it will be another 0.4 second. So total will be 0.8 itself. Okay, so between the obstacle, okay, so for the speed is 320 meter, 320 meter per second. Speed is distance divided by time. Okay, if I want to find the distance between the obstacle and the bat, okay, so the time taken I will use is actually 0.4, just 1 trip only. Okay, so distance will be here. Distance is here. Time will be 0.4. Speed will be 320 meter per second. So if you look at algebra, you should allow you to arrive at the answer to be 128 meter. Okay, remember here the trick about using echo, to take note of echo is the time or the distance required. Does the question give you a time or distance? Does it Does it give you a time whereby it's a two-way trip, go and come back, or does the time actually given is only one-way trip? Okay, so it depends on the question itself. So look at the question carefully. Okay, sometimes the question, instead of giving you 0.8 seconds, it actually give you 0.4 seconds. Okay, for one-way trip. But the question mentioned is echo. So echo will be 0.4 go, 0.4 come back. So total will be 0.8. It depends on what is the question that's given. Okay, so take note when you're dealing with echo. Okay, 16 is electrostatics. I would say it's quite straightforward, where I gain charge, I lose electrons, I gain electrons. Okay, the more I lose electrons, I will be positive charge. I gain electrons, I will be negative charge. Okay, so I will not dwell too much on question 16. Now, 17, the formula that I mentioned quite often, okay, other than V equal IR in circuit, okay, power equal to IV, all this formula, there are some small formulas that we need to take note. For example, current is actually Q over T, charge per unit flow of charges. Voltage, potential difference is energy per unit charge. Resistance is, there's a formula for it, will be rho L over A. So these are the small formulas that you have to pay attention to, because these formulas sometimes it will assist us in making the correct calculations. Okay, for example, in this case, okay, the voltage is, the EMF is, potential difference is 3.0 volts. Okay, there's a charge of 15 coulombs. What's the amount of energy given? So if you look at the formula, energy, charge, and voltage, you can easily arrive at this formula. So if you substitute the value inside, for example, voltage is 3 volts. Okay, energy is what the question is required to find. Charge is 15 coulombs. Okay, so you'll be able to arrive at the answer will be 3 times 15. Okay, it will definitely give you a straightforward answer to be 45 joules. Okay, so answer will be D. Okay, so take note of the formula. If you forgot about the formula, that I would say it's quite very difficult to actually get the answer. Okay, so the formula is important. Okay, same thing. The formula, question 18 we will look at is, if I'm not wrong, is R equal rho L over A. Okay, which of the value give the smallest diameter, smallest reading in ammeter? Now, for the ammeter, for the current to be small, okay, one of the characteristics it must be is that the resistance must be large. Okay, so for resistance to be large, okay, the radius, the diameter, everything will have to change accordingly. So the formula that we are looking at will be R equal to rho L over A. So I want basically what for resistance to be big, okay, given the same piece of wire, okay, for this to be big, my length must be large. Okay, the length must be large. Okay, so that my resistance can be large. For my resistance to be large, my area has to be small. Okay, the denominator has to be as small as possible. Okay, so we are looking at the numbers. We are looking at the number here. So if I want the length to be big, okay, so looking at the choice, okay, if I want the L to be big, so big L will be these two numbers. I want my area to be small. Basically, my diameter must be actually also be small. Okay, so large length, big L, small a or small diameter. So automatically, the answer will be D straight away. Okay, why? Because I want my resistance to be large. Only when resistance is large, current can be small. Okay, remember current and resistance is an inverse relationship. So this is how I derive my answer quickly. Okay, so know the basics. Okay, know the conditions, know the basics. Okay, compass needle between two bar magnet. Okay, remember one of the characteristics about compass magnet is this compass needle actually points or represent the direction of field lines, the direction of magnetic field lines. Okay, so this is the characteristic of your why we use a compass. Okay, so if I say the compass point to the right, I'm literally saying that the magnetic field actually point from A all the way to B. Okay, so this is what we mean by your magnetic field line. This is what does the compass represent. So you'll be pointing from A to B. Okay, and same thing, if you know it's from A to B, and we always know that field lines come from north. Okay, so effectively, I'm saying that with the few line drawing, I can actually deduce A is north, and likewise, B will be south. Okay, so B is south, B is south, A is north, only this answer. So question 19 will be A. Okay, so take note of this. The characteristic that, or the question that's testing is about students' understanding of magnetic field lines. What does magnetic field line means? Magnetic field line means two things. It means the field lines actually come from north, go to south. The other aspect that the question expects students to know is that what does the compass needle means with respect to the field lines? Okay, compass needle, okay, it actually points to the direction of the magnetic field line. Okay, it represents the direction of the field line. So this is what the questions require the students to know. So take note of this. Okay, it's quite a common thing. Okay, right, the basics of magnetism. Okay, 20. If you look at the particular question here, we look at wires, we have current, especially we have current, and I need to know the compass needle, direction of compass needle at X, aka the question is actually asking for the direction of the field lines. Okay, remember compass needle, the purpose of using a compass needle is to actually represent the direction of the magnetic field line. Okay, that's the purpose of the field line. So basically what the question wants is, the question wants to use the student to find with the current, okay, locate the direction of field line. So from current, I want magnetic field line. Okay, so once you know current, I want magnetic field line, this relationship, it will mean that this will require you to use Maxwell right-hand grip rule. Okay, because Maxwell right-hand grip rule involves is a representation of your current to your field lines. Okay, so the moment you have current to field lines, only the aspect. Okay, straight away you know you use your right-hand grip rule, you grip the current. Okay, so if it's a solenoid, the coil will represent the current here, and this is where your fingers will actually grip. Okay, your fingers will be gripping this coil, and you'll find that your thumb will actually point in this direction. This is where your thumbs will point. This is where your thumb will point. Your thumb represent the North Pole. Okay, the thumb will represent the North Pole. Okay, so if I represent the North Pole, it will also means the field line is coming from the north. Okay, from my North Pole is going towards A. So my compass needle will definitely be pointing towards A. Okay, so that's why the answer is A. Excuse me, sorry. Okay, so take note of where the North Pole is pointing. Okay, North Pole, the thumb represent the North Pole, and North Pole usually where the field line is coming out from, and it also means is where the magnet is going to be pointing at. Okay, so that's why the magnet will also point towards A. Okay, in the direction of the field line itself. Okay, so with this, okay, this is the last question for paper 1. Okay, for paper 2, okay, paper 2, same thing. Paper 2, yes, quite a good question inside here. Okay, paper 2, okay, some of the questions inside are actually quite demanding for the students, but it challenge the students' thinking. Okay, so I would say it's a good paper. Okay, but there are some gaps that sometimes students will tend to forget when they look at the paper. Okay, now for example, question 1A, I will not dwell too much. A part 2 is the one that I would say is quite interesting question. It's a good question actually. It's something that we tend to forget, especially when we always think that scalar and vector is always so simple. Okay, question A part 2 dealt with the basic of vectors and scalar. Okay, now in the circular track, okay, whereby you look at constant speed, okay, the Chpt is jogging around a circular track in circle. Okay, so jogging around in circle. Okay, oops, sorry, let me draw okay, can. Okay, so you're running around in circle. So the speed, the speed of the guy, okay, is actually, the speed is actually, okay, 1 meter per second, okay, around the track. Okay, but based on the question is there is an acceleration. Okay, there is an acceleration, okay, experienced by Chpt. And what the question means is that for him to have an acceleration, it also means that there is a change in velocity. So for acceleration to exist, okay, there must be a change in velocity. Okay, but yet, okay, the question says the speed is constant. Okay, here is where the question demands the students to actually know the difference between scalar and vectors. Okay, for scalar is what we understand is it only has magnitude. Okay, vectors you have magnitude and directions. Okay, so although Chikyong is having a constant speed, but because he's running in circle, so the direction of each of his path, direction of his travel, direction of jogging, at each motion, okay, at each of his jogging when he turn in circle, okay, the direction is actually there's a slight difference there's a slight change in direction every time. So even though the speed is the same, you will find that okay, the direction of Chikyong is always changing. Okay, and because direction is changing, even though the magnitude remains constant, Chikyong velocity is changing. Okay, even though the speed is the same. Remember, I repeat again, because Chikyong has a changing velocity. Why? Because even though his speed remains the same, but the direction of his run or his traveling is actually changing every time. While he travels, the direction is always changing. And because direction is changing, even though I have the same magnitude, okay, it still contributes to a new vectors every time. And that vector is what we call velocity. Okay, and because velocity is changing, aka there will be acceleration experienced by Chikyong. Okay, because acceleration involves change in velocity and velocity involves change in magnitude and direction. Okay, so that's why he definitely has an acceleration. Okay, so this is where the questions require the students to take note of what do you mean, what does it mean to be having a accelerations, having a constant speed. Okay, but yet the question is asking students to infer the fact that Chikyong is having a changing velocity and aka an accelerations. Okay. Now for 1B, okay, car and truck, okay, along the same point, traveling along the same road in the same direction. Okay. Now truck is having a constant speed. Okay, describe the motion of the car. Okay, in the first 8 seconds. Same thing. When we talk about description, okay, always remember when we talk about description, okay, talk about description, always describe the acceleration. Okay, not the speed. Okay, not the whether the speed is changing or what, not about the speed is increasing from 5 seconds to 5 meters per second to 10 meters per second. It's not always about the speed. Okay, when you talk about description, it's always talking about the answer always requires the student to talk about the acceleration. Okay, constant gradient. Okay, constant acceleration. Okay. Now, so take note of this. It's a very common question, which I would say is a very, very basic of kinematics, whereby students need to know actually how to describe the graph itself. Okay. Now, in terms of forces, how is it possible to move at constant speed? Definitely constant speed, or sometimes we call this terminal velocity. Okay, it could be terminal velocity. Okay, is whereby it has only one one motion. Okay, remember whenever I talk about whenever we talk about constant speed, when we talk about forces, you always have the standard keywords that we look at. We deal with using Newton's law. So you need to talk about the net force. You need to talk about the acceleration experienced by the object before you can conclude the velocity experienced by the object itself. For example, if the questions conclude that you have a constant speed, okay, the question will actually require the students to actually infer when the object is traveling at constant speed. What does it mean? It actually will mean that the acceleration of the object experience will be 0. And what's the cause behind 0 acceleration? I also require the students to know that, okay, because the net force experienced by the object is actually 0. And one last thing that I can infer, or I need students to infer from all this, is that net force 0, it will actually you actually represent that the forward force, okay, is equal to the forward force, or the applied force is actually equal to the friction. Okay, so these are the 4 things that I would require the students to actually infer. Okay, equal. Okay, so whenever the questions talk about constant velocity and he wants you to make representation or reference to the forces, okay, there are certain keywords that must be present. For example, I will require the student to talk about the net force. and talk about acceleration, and eventually talk about what happened to the forces in particular, okay, or in context. In this case, it will be the applied force, okay, or the force acting on the truck, and the friction acting on the truck itself. So the both of them will be equal, okay, and you will experience a resultant force, and the acceleration will be 0. And because of that, I can deduce that it is moving at constant speed. Okay, so you look at the keywords that we are looking at for whenever we deal with forces pertaining to constant speed or terminal velocities. These are the 4 factors or 4 keywords that I will require students to write. Okay, so it's a standard template that students need to take note of it. Now, calculate the distance between the truck and the car at time 8 seconds. Okay, so basically for speed time, velocity time graph, whenever I look at the distance, you will definitely be looking at what we call area under the graph. Okay, area under the graph. Okay, so what area are we looking at? The truck and the car at 8 seconds. Okay, 8 seconds. Okay. How far are they? What example for the car? The distance will be here. The car area under the car will be this triangle. Okay, so I will require you to find the area of the triangle, which is the distance of the car traveled. And for the truck, okay, area under the truck graph will be this. Will be this blue color line, which is the rectangle. Okay, so you'll be a triangle minus the rectangle. Okay, so if you look at the difference, okay, you will find the difference in the distance between the 2 objects, which is why I'm looking at the triangle followed by the rectangle. Time whereby the truck meets the car meets the truck again, same thing. Basically, I'm looking at catch up. Okay, the time whereby I need the car catch up with the truck again. Okay, in this case, for the car to meet the truck, okay, based on the part 3 answer, okay, the car is actually lagging behind, okay, the truck by 40 meters. So for the car to meet the truck again, he must complete, or the car must overcome 40 meters after 8 seconds. Okay, so now let's look at where is the 40 meters. Now, in this case, okay, after time 8 seconds, the car is here. After 8 seconds, the car is lagging behind the truck by 40 meters. So which means that for the car has to cover an extra distance of area here that's equivalent to 40 meters. Okay, using the speed here. So the area here that allows him to cover 40 meters for the car here, it will mean that the area of the shape must represent, okay, 40 meters. And for this shape, okay, for the shape, okay, the breadth of the shape will be, this is 5 meters per second. Okay, based on the graph here, this is 5 meters per second. Okay, time, okay, I don't know the time, but I do know that the area for this graph will be 40 meters. Which means the area for this shape will be what we call 5 times t. Okay, length times breadth. Okay, and I will know that the time for me to travel the extra 40 meters will actually be 40 divided by 5 will be 8 seconds. So the car will definitely need another 8 seconds. Okay, for the car to catch up, another 8 seconds. So in total, okay, at 8 seconds, I am actually 40 meters away. So I need another 8 seconds to catch up. So total time I need to catch up will be 16 seconds. Okay, to catch up for that, to make up for the additional 40 meters. Okay, so this total time needed will be 16 seconds for the car to meet up with the truck. Okay, so this is where the marker or the setter will actually require the students to actually analyze, okay, the question, the graph itself, to get certain to get the values, to get the difference in area, to get the additional 8 seconds appearing, okay, in the working. Now for question 2 about CG, okay, mark an X on the possible location of CG. Okay, is whereby CG is always the point whereby all the mass are equally distributed. Okay, so it's roughly around here, like what I mentioned in the question, it will be here. Okay, weight is always vertically down. Okay, so the answer will be here. Okay. Now, same thing is the question asks for what happens when I fill up the water, okay, in the glass. Okay, now if I fill out the water in the glass, take a look. Okay, if I fill out the water in the glass, means now if I fill the water with the glass, sorry, I fill the glass with the water, you'll find that now the top is heavy. So after filling up water, okay, the top of the glass is actually heavier. So what you do is for CG, you will actually make sure that the all parts of both section or both lines or CG will be a point whereby all the masses will be equally distributed. And because now the top is heavier, so now the CG will no longer be here already. The CG will no longer be at this location, and as a result, the CG will actually be higher. Okay, so let's see if I fill out with water, the CG will actually move higher. Why I need to move higher is because only after I move higher, okay, then I will be able to redistribute the mass such that the bottom side of the glass is actually equally heavy as compared to the top side of the glass here. Okay, with the water. Okay, this is what we mean by redistribution of the weight. CG, what the location of CG actually talk about the redistribution of weight such that, okay, the weight is actually equally distributed from that point onwards. Okay, and same thing because now my CG is actually higher. Okay, now my CG is actually higher. What does it do? What's the impact? Okay, with the CG higher, it will make the glass topple more easily. Okay, or it will make it less stable. Okay, so this is what we mean by the effects of your CG and the effects of CG on your stability. Okay, and because the CG will actually move higher because now the top is heavier. Okay, same thing, one modification, any reasonable one, it could be larger stem, bigger base, etc., etc. So I will not do too much here. Okay, question 3, the refrigerations. Okay, cooling unit, black fins. Take note here, we look at black. Okay, so if you look at the color here, we're definitely looking at radiations. If I'm looking at metal, okay, I'm looking at the color. So let's say I'm looking at color. Okay, so before I look at the question, I will see how the questions give me. Okay, expect me to look at what are the different mode of heat transfer. If it's color, it will definitely be radiation. If it's metal, okay, metal, okay, you talk about material. If it's material, usually it involves conduction. Okay. Containing fluid, okay, may be talking about convection fluid. Okay. We talk about cooling units, the location of this cooling unit. Okay, this is at the top side. So the moment we talk about location, we could be looking at convection current. Okay, so these are the possible things that we are looking at. Okay, we are possible heat transfer. Okay, so now we look at the question. The question asks, explain how the black metal fin remove heat effectively. Black metal fins. Okay, black metal fins. Okay, so we are looking at two mode of transfer. How do I know it's two mode? Because black metal. Black is actually talking about radiation. So the moment we talk about black, okay, the mode of transfer we are looking at is looking at radiations. Okay, so because it's a hot, how does it remove heat effectively? Okay, from the pipe. Okay, it has to be emitting the air out, emitting the heat, thermal energy out. So it will be acting as a good emitter, okay, to actually emit the heat out from the environment. Okay. So when we look at black, okay, we are looking at radiations. Okay, so it depends on what you're looking at. Okay. Indirectly, I'm also saying that, let's say the fins is actually releasing the heat faster. Indirectly, he also said that it could also be absorbing the heat from the pipe, okay, faster. So I can also phrase it in the way whereby black refer to it as an absorber, okay, absorbing the heat from the pipe. Okay, so if it's an absorber, it is from the pipe. Okay, from the pipe, heat from the pipe. Okay. Then after that, if it's black fins as an emitter, it will be after absorbing the heat from the pipe. Okay, you'll be releasing the air, the heat, okay, to the surrounding. So it's like a two-way process. It's one side you'll be absorbing the heat. Okay, absorbing the heat, he'll be acting as a good absorber. Okay, absorbing the heat from the pipe. Okay, then the other way as an emitter is that fin will be releasing heat to the environment. Okay, so this is where how radiation actually take place concurrently. One side will be absorbing and the other side will be actually emitting. Similarly, when you look at matter, okay, matter we talk about is a conductor. Okay, yeah, it talk about heat being conducted out from the fluid in the pipe to the surrounding effectively. So here we are looking at conductor. Okay, so keywords we are looking at is when we talk about conductor, you must talk about conductor, you must talk about heat being conducted. So conductor, conduct, these two keywords are actually tagged together. So this is where I actually require the students to explain in details what do I mean by black fin, black matter fins. Okay, so the black is radiation, the matter refer to mode of conduction. Okay, cooling down the compartment, definitely cooling down the compartment. The cooling down, like I mentioned before, you talk about location. Okay, and location we only look at convection current, and convection current we look at hot rise. And remember, hot rise, cold sink, not just this way. Hot rise, cold sink is just one set of keywords. The other set of keywords that we're looking at is the density change. Okay, so when we talk about hot, you need to talk about less dense. When you talk about cold, you need to definitely talk about sink and definitely talk about the density of the liquid. Okay, so the density of the air here we are looking at, okay, it refers to convection. And convection, there are three sets of keywords. When we talk about hot, you must talk about density. When you talk about cold, you must talk about density also. So after that, you can conclude that there is a convection current occur. So the keywords that we look at, the tagging keyword is actually quite standard one, whereby we look at the density changes, okay, pertaining to the hot and cold air. So the tagging keyword, hot, less dense, cold will be denser. That's the first set of keywords. Thereafter, we talk about whether it's rise or it's sink. Rise or sink. And followed by the third set of keywords, whereby the convection current actually created is being set up. Okay, repeated. Now for question 4, okay. Okay, for question 4, okay, question 4 we deal with transverse wave. You look at waves, okay. But particularly this wave, we have a, if you look at the picture, there's a deep area, there's a shallow area. Okay, and if you look at the pictures or what the picture is trying to tell you, other than the area, we're also looking at the wavelength. You look at the question here, the wavelength of the wave, okay, in the deep area, and we look at the wavelength in the shallow area. Okay, there's a difference in wavelength. Okay, the wavelength in the deeper area is actually larger, longer, as compared to the wavelength in the shallow area. Okay, so this is what the clue the question is trying to tell you, is talking about the waves in the water wave in the deep area, in the shallow area. You're talking about the wavelength in the deep area and the wavelength in the shallow area. And one of the things that's hidden behind this question is that because the whole questions revolve around the medium water, it's the same medium. Okay, so we can actually effectively conclude that the speed actually remains the same, whether it is shallow or deep. Okay, so the speed, actually the velocity of the wave actually remains the same. Okay, now for this aspect here, okay, this is one of the common things that we tend to make this mistake. Okay, now the question that we're looking at is that the first, if you assume that the speed remains the same, okay, this statement is actually the first mistake that you will make. Okay, so in fact, okay, when we look at the waves at different area, the speed of the wave actually will change. Okay, same medium, okay, it doesn't mean that the wave actually remains the speed of the wave remains the same. No. Okay, so even though in the same medium, but actually the fundamental aspect of the environment actually has changed. It has gone from a deep water to actually a shallow water, shallow regional water. So environment actually has changed. So we cannot say that the speed actually remains the same. Okay, so what we does is actually what we can conclude is that whether the wave is moving from deep area to shallow area, okay, the speed will change. Okay, the speed will change, but what will remain constant is actually the frequency of the waves. Okay, in this case, frequency of the wave is like I would say like your IC number, like your code like that. Okay, if it's the same wave, the frequency will actually remain the same. If it's the same person, the code will actually remain the same. So I will say that the one that we can conclude with certainty is that the frequency of the waves, okay, is actually remains constant. The speed, okay, will definitely change because the context of the environment actually has changed already. Deep area to shallow area is definitely two different areas already. So that's why the speed actually will change, okay, but the frequency actually remains the same. Okay, so note the common pitfall here that the student tend to make. Even sometimes I myself may also make the same mistakes here. Okay, so take note of the I would say the assumption here. Okay, whether the speed remain the same, frequency remain the same. The students, you have to actually know what you are doing. Okay. Now it takes 0.2 seconds for the dipper to move up and down once. Okay, up and down once. Okay, so this is what it's looking at now. Okay, so up and down means what? From up to down. Okay, so there's one cycle here we were looking at. Okay, so the wave generated move up and down. Okay, so for frequency, I would say it's quite straightforward. If you know the period is 0.2 seconds, okay, you will know that the frequency will be 1 over period. It will be 0.2 inverse of 0.2. It will be 5 hertz. Okay, same thing. Notable change, like I mentioned before. Okay, based on the question, based on the question and based on the picture, you can actually deduce what are the changes. The change in amplitude. Okay, the change in amplitude. Okay, the change in amplitude. Change in amplitude. Okay, larger amplitude, shorter wavelength, or even you can say, okay, from deep to shallow. Okay, the speed of the waves actually decreases. Okay, you can conclude these three observable change. Okay, now state and explain the change in speed. Oh yeah, okay, since the question mentioned part 4 is change in speed, so I can't do that in part 3. Okay, if not, I'm just repeating the answer. Okay, so part 4 mentioned, okay, what is the change in the speed? Okay, like I mentioned before, the speed will decrease. Okay, why? Because the wavelength actually decreases based on the picture. With frequency remain the same, okay, the speed actually will decrease. Okay, based on the formula V equal to F lambda. Okay, take no assumption. Okay, here what we are deducing is, remember, medium, although same like sound, okay, sound, the medium remain the same. Okay, for water, for waves, same as sound. Okay, if the medium remain the same, the speed of the in that medium should actually remain the same. But what happened now is that the medium that we are in contact in the question here actually is not it's not the same, because we are looking at water, yes, but just about now we are looking at the water in the deep area and water in the shallow area. So in terms of context, okay, they are actually two different separate environment. Okay, so take note of it. Similarity and differences between the wave properties and sound wave. Okay, this one I would say that is a very standard answer for textbook. Okay, from textbook, basically what they are trying to tell you, trying to ask is difference between transverse wave, okay, versus longitudinal wave. Okay, so it can be transverse wave, could be the vibration is perpendicular, longitudinal could be parallel. So these are the common differences. Similarities, I would say it's straightforward because there's only a few similarities, and one of the common one that we always like to use is both ways actually transfer energy, okay, from one location to another location without the the molecules moving. Okay, so this is one of the common similarities that we have to take notes. For question 5, Redrawing diagram, you have an object which is here. Okay, now the focal point given in the length is F1 and F2. Okay, so draw two ray diagram to locate the image. Okay, now ray diagrams, ray drawings, I have, if you have forgotten, okay, you can revise, you can look at the what I call the video that I make on ray drawing diagrams. If I don't know, I have made 2 videos on ray drawing diagrams, so take note of it. Okay, you can refer to it in my description panel below. Okay, or click on the link that I give provided below also. Okay, you look at how you draw the ray diagrams. For ray drawing diagram, there is a standard approach. Usually what I do is I will actually draw ray 1 first. Ray 1 usually, what is ray 1? Ray 1 refer to where? The ray that coming out from the object, cuts through the optical center, and it goes straight through without bending. This is ray 1. Okay, so same thing, it comes from the object, go through the optical center without bending. Okay, so this is the first ray I draw. Second ray I draw, if you like, okay, I can draw ray 2, which is the parallel ray. It hits parallel ray, it hits the lens. It hits the lens. After that, what it does, it actually cuts the focal point. Okay, it cuts the focal point and it cut the focal point and goes straight all the way. Okay, so this is the bend that we are looking at. Remember arrow, and with this you will find that okay, the intersection point will be the image itself. Okay, you can draw the image which is upside down. Okay, if you don't like to draw ray 2, you do like to draw red color one. Okay, you can draw ray 3. Ray 3 will be it cuts the focal point first. Okay, it cuts the focal point. Okay, then what it does, it cuts the focal point, and after that it goes straight through without bending. Okay, so it depends on which ray you want to draw. Okay, so it depends on which ray you want to draw, the answer will actually remains the same. Okay, so take a look at which ray you want to draw. Okay, ray 1, ray 2, ray 3. Usually confirm one I will always draw is I will always draw ray 1. Okay, ray 1 I will always draw because sometimes I like to use ray 1 because ray 1 actually also allows me to locate the lens direction of the lens or the location of the lens itself. Okay, then after that you can draw ray 2. Oh, too much. Okay, draw ray 2. Okay, if not, you can draw ray 3. Okay, I'll leave it to you whether you want to draw ray 2 or ray 3. But I always have a good habit to draw the ray diagram. Okay, and after that, okay, remember to draw your arrows. Okay, lines with arrow is called ray diagrams. Okay, with no arrow, it's just called a straight line only. Okay, so take note of the drawing. After that, okay, draw the label, the image, I. Okay, the pattern that we look at. Okay, then after that, 2 characteristics formed by the image here. Okay, this one I would say look at the drawing, you will know it's inverted and diminished. 2 changes to move the location of the lens. Okay, so for the changes, okay, still 2 changes for the image when the object move nearer between the lens and the focal point. Okay, move to a location between the lens and the focal point. So between the lens and the focal point means it's actually object. Okay, whereas the object is actually less than the focal point. Okay, if it's less than the focal point, it will imply, okay, it will mean that the object, okay, the image produced at this location less than focal point. Important thing is less than focal point. Okay, means the object, the image form, it will be magnified and it will be virtual. Okay, because this is what we mean by the ray diagram. In the ray diagram that we have 6 ray diagrams. Okay, we have 6 ray diagrams, and one of the ray diagrams that we have is actually the object less than focal point, which is what the question is trying to tell us. Okay, so less than focal point means in between the lens and the focal point means it's actually less than the focal point. Okay, and as a result, it will be enlarged, it will be magnified, or it will be virtual. Okay, so this is whereby I always advise students to actually know all the 6 diagrams. Okay, know them, understand them. Okay, so that when questions like part C, okay, give you actually can call out the correct diagram in your head, okay, in the mind, and actually locate the correct outcome or the correct image property. Question 6. Okay, question 6. Okay, we have resistance in parallel. Okay, it looks like it's in parallel. It looks like all the 3 are in parallel at one look. Okay, so but be careful of the arrangement. This 2 is in parallel. Yes, definitely. Okay, but take a look at this. Okay, they are not in parallel. It doesn't mean up and down is parallel here. Okay, in fact, this 2 ohm actually is beside the 9 volt the battery. So if you can't see what's the arrangement for 2M, okay, my advice is actually to draw the cable to actually redraw the circuit. Okay, so let's take a look at this. So I'll keep 10 ohm here. Give me a minute. Okay, so I'll keep the 10 ohm here. Okay, so this arrangement, okay, is here. Okay, so what I do now is I will actually straighten this cable. Okay, make it horizontal. Okay, so you'll be here. Wait, give me a minute. So I'll straighten the cable. You'll be here. Okay. Then after that, 2 ohm resistor, I'll put here. Okay. So what I do now is actually I will actually lengthen this cable. So now I will lengthen this cable. Okay, so I'll extend this cable to here. Okay, so what I do is I lengthen the purple color cable. Okay, I lengthen the purple color cable all the way, and the end of the purple color cable is actually connected to the cells, okay, to the battery. Okay, so this is the purple color cable. Okay, then the black color is here. Okay, I'll highlight here. This cable. Okay, it's actually here. Okay, so this is what I mean by I rearrange the circuit here. Okay, so now my 9-volt battery is here. Okay, so what I did was I actually rearranged the circuit. Okay, but remember what I done is, although I say I rearrange, but it doesn't mean I disconnect everything and reconnect everything. No, what I did was I just shift the location only. I just shift the arrangement. I still keeping the connection between the resistor remaining the same. They are still connected to the same place. What I do is I just lengthen the wires. For example, I could like maybe make the red color cable. Okay, I make a red color cable here. Okay, I flatten it. Maybe I make it horizontal to become this cable. They are actually the same. Purple one, I actually lengthen it. Okay, I actually lengthen the purple color one. Okay, and it becomes this arrangement. So if on the arrangement on the right, you'll see it's quite, I would say it's quite clear to say that this two is in 10 ohm is in parallel to each other, and my 2 ohm resistor is actually in series with the parallel arrangements. Okay, so this is what we mean by the actual arrangement of the circuit here. Okay, so once you know is series and parallel and series arrangement, you will be able to find the parallel arrangement. You will be able to find the effective resistance, or what we call the total resistance. Okay, this is parallel branch, R parallel, plus the 2 ohm. Okay, this is the total arrangement. Okay, so I will not deal with the math. So by now, you're finding effective resistance, I would say, is quite fairly straightforward. So parallel arrangement will be here. This is the R parallel. Okay, so this is what the circuit look like after you redraw it. Charges flow through the 2 ohm resistor in 10 minutes. Okay, same thing. Charge, if I want to find charges, there's only one formula, Q over T. Take note, T has to be in second. So your 10 minutes has to change to second. So you must change your 10 minutes to second. 10 minutes times 60, it'll be 600 seconds. Okay, so now before I use the formula, the question asks for Q. Okay, so it'll be Q equal to IT. So I have the time. So now what I lack is actually the current. So I need to find the current in the 2 ohm resistor. Yeah, 2 ohm resistor. The easiest one I will look at is 2 ohm resistor. The current in the 2 ohm resistor is here. This is the current in the 2 ohm resistor, which is also the current in the total circuit, okay, flowing out of the battery. Okay, so if I know the effective resistance, okay, if I know the total resistance, I can find the total current flowing out of the battery because I know the total potential difference, which is the EMF. Okay, which is my 9 volts, IT plus 7 ohm. okay, which is here. Okay, 7 ohm is here. Okay, and after that, I will have the answer to be 1.29. Okay, once I have the current flowing from the battery, which is also the current in IT. So here, IT, okay, if you find IT, which happens to be 1.29 amp, which also happens to be I2. Okay, because they are the same current. Okay, this number here, okay, you substitute into the equation, okay, which is what you get here, which is 771 charge coulombs. Okay, so this is the equation that we're looking at. So for this part B here, we are looking at two-step process. You need to perform the first calculation to identify the current first. Then after that, you need to apply the second formula to look at the charges, to calculate the number of charges. Okay, so it's a two-step calculation. Now, question 7 here. Okay, question 7 is a slightly complicated circuit. Okay, whereby I look at the live wire and we look at the neutral wire. Okay, how the live wire? Okay, and each of the lamp, they are identical lamp. All the lamp are identical. 240 volts, 80 watts. Okay, power supply is 240. Yeah. Now, state advantage of lamp connecting in this manner. What manner am I talking about? Okay, you look at the arrangement. If I have current flowing from the live cable, what arrangement am I talking about? When I flow, okay, when I flow, okay, I will go through. After that, I will split. My current will split. Okay, so when I talk about current splitting, it's actually about parallel circuit. Same thing, the current will come, it will flow, it will split again. You go to light bulb C, it will continue. After that, it may go to light bulb B, or again, it may go to light bulb A. Then after that, it go back to the arrangement again. Okay, now you look at the circuit here, you'll find that, okay, you'll find that the current that we are looking at, okay, the current that we are looking at, okay, it actually split up, okay, it actually split up. So when we talk about current splitting, okay, the arrangement that we are looking at is actually a parallel arrangements. Okay, so one thing of good about parallel arrangement, once you identify its parallel arrangement, the good thing about this is that one light bulb, if it's spoiled, okay, the rest of the light bulb actually is not affected. It will still remain as per normal and life still go on. The light bulb will still work. Okay, that's the advantage of this. Okay, now there is a light bulb that is connected, okay, in the unsafe manner. So which light bulb is it? Okay, unsafe manner meaning what? Okay, now remember when we talk about unsafe manner, with example, fuse. Fuse has to be connected in live cable. Switch, okay, okay, your switch, okay, your switch, okay, must always be connected in the live cable. Okay, your switch must always be connected in the live cable. C is the only switch whereby it's the only light bulb whereby the switch is in the neutral cable. Okay, it's in the neutral cable. Okay, remember your fuse and your switch has to be on the live cable. Why? Because it has to be on the live cable so that I can disconnect the appliances from high voltage when it's switched off. Okay, so what happens is when it's not on the live cable here, if you the switch on the neutral cable in this case, okay, even if I switch off the lamp, if I switch off, the lamp will still be connected at high voltage. And if it's connected to high voltage, means there is a chances that somebody touch the lamp, that person will get electrocuted easily. Okay, so that's why it's one of the unsafe arrangement that we're looking at. Unsafe arrangement is in terms of the location. And location-wise for live wire, two things that has to be connected on live wire is your fuse and your switch. Okay, so these two you have to be careful. Okay, the fuse and the switch has to be on the live cable here. Now calculate the current going through a fuse. Okay, where is the fuse first? This is the fuse. So what current are we looking at? Is the current, okay, in the total current that's flowing through all the circuit. Okay, and this current actually is broken down into 5 current. Okay, why? Because there are 5 lamps. Okay, so to calculate the 5 current, all you need to do is calculate the current in each lamp. Okay, and each lamp you are given is, if you switch on everything, okay, each lamp is 240 and 80 watts. Okay, so you use the formula power equal IV. Okay, power equal IV. Okay, you can calculate the current in each lamps. You multiply by 5, you get the total current in the circuit, which is 1.67. Okay, which is 1.67 here. So this current here will be 1.67 amp. Okay, so the current going through 1.7 amp, and so what's the fuse that's needed? Okay, so the fuse rating will be 2 amp. Okay, the next best rating or the next highest rating that we have will be next best rating. The next available rating will be more than 1.67. It will be 2 amp fuse. Calculate the total energy cost. Okay, remember we're talking about energy costing. Okay, energy costing, we talk about energy needed. Energy needed has always to be in kilowatts hour. Okay, and we talk about kilowatt hour. Okay, energy is power times time. So which means my power, the unit for power must be in kilowatts. Time, it has to be in hour. So 30 minutes will actually be half an hour. I got 5 lamps, so I need to multiply by 5. This is 5 lamps. 80 watts, I change to kilowatt, will be divided by 1000. Okay, so I will know that for 5 lamp, I will require 0.2 kilowatts. And if I know that 1 kilowatt is 18 cents, okay, 0.2 kilowatt, it will actually give me 3.6 cents. Okay, quite easily done. Okay, take note of the calculations, especially the tricks whereby we deal with kilowatt hour. Okay, especially kilowatt. Remember to have a habit to change it to kilowatts. Now for question B, section B, question 8 is another circuit question. Yes, but this time around the circuit has a bit of magnetism involved. Okay, so it's a circuit plus magnetism. Okay, electromagnetism. Okay, so now one thing to take note is that when you look at electromagnetism, when you look at diagrams, okay, take note of all the labelings. Okay, this labeling has certain impact on it. Okay, for example, okay, when you look at coil, okay, when the question gives you coil, what does it try and tell you? Especially coil with iron core, these two combined. Okay, means this arrangement, the question is trying to hint to you that maybe if electricity passes through the coil, I will be able to get an electromagnet appearing. Okay, so this maybe what the labeling is trying to tell you. Then after that, the question talk about pivots. When we talk about pivoting, we are already talking about maybe that the particular object, the lever, okay, the lever is able to swing up and down. Okay, the swinging is, okay, able to swing up and down, or able to swing, I would say up and down lah. Okay, that's what the question is trying to tell you when I say lever. Okay, reset button here. Okay, reset button here. When the more I see reset button, I'm looking at something that I'm able to push. Okay, push in and out. Okay, then when I talk about spring, when there's a mention of spring, it's usually controlling, maybe like pulling back. Is the purpose is to about pulling back something, pulling back. Okay, and after that, springy metal. Springy metal is about maybe this piece of metal allow me to move, okay, or bounce in a certain direction, maybe swing left and right, up and down, depends on the motion. After that, fixed point, usually I would say it's quite straightforward to say that it acts like a pivoting point. Okay, so it acts like pivoting for something. In this case, it's actually for pivoting point for the springy metal. So I would say, when you look at the pivoting point, so it's more like, it's a purple color. Yeah. So the pivoting point and the fixed point, springy metal, they are like together, whereby they are together. There will be like maybe swinging left and right, swinging left and right. Okay, so that's what maybe the labeling is for. Okay, so the labeling are there for a reason. So before I start to look at the question, at least appreciate the labeling to see how it works. Okay, so in the sense that, okay, what happened is could be like the current could be coming in. Okay, the moment I run through the current going through a core, it becomes an electromagnet. Okay, so the current will still be going through. So at the same time, whereby it becomes electromagnet, it's trying to attract this particular iron lever. Okay, iron lever is attracted, so you will move up. Okay, so but before you move up, you take a look, the current is actually continue to flow. At the same time, the current is actually flowing down here, go down all the way through the contact point. Okay, after that, go up, and after that, exiting the circuit. Okay, so at the normal flow, it looks like this. Okay, so now what happens is when the current actually, the solenoid, the coil and the iron core become an electromagnet, it attracts the iron core, it attracts the iron lever, it moves up. So when it move up, you'll find that this spring will actually pull this springy matter to the right. Okay, so the moment I spring to the right, you'll find that this contact, whenever I see contact, I will know that there is something to do about breaking the contact, or it could be forming the contact. Okay, so the moment the spring pull the springy metal to the right, the contact is broken, the current will be cut off. Okay, so then after, where does the reset button come in? Okay, so remember, once I pull the cable, once the springy metal pull the bouncing, once the spring pull the springy metal, the piece of metal here will be to the right. So this piece of metal will be to the right. So this piece of metal will be more to the right. Okay, so what I do is the reset button will actually act as a push. Okay, to push the springy metal to the upright position again. So it becomes this position again, and the contact will be formed. Then after, the current will flow again. So this is how a simple circuit breaker works. So before I look at the question, I actually try to appreciate the drawing first. And when I say appreciate the drawing, to actually understand how the whole circuit works. And when the whole circuit works, it doesn't mean I start from scratch. I look at hints that's given. Example, the hints, which is all the labelings. All the labeling here, what does it mean? And actually, I look at the current. There's a starting point given in the question. There's the starting point here. So I actually start from the clue there. So I don't start from anywhere or anyhow. Where I actually look at the question and see what are the clues that's being embedded inside the question. Okay, so like I mentioned before, okay, how does the circuit works? Okay, so if you actually analyze the circuit, you should actually able to answer 8A straight away. How does it work? Okay, maybe you look at some of the keywords. Whenever you look at iron core and coil, okay, you like to use the word magnetize, it becomes a magnetic. Okay, then after that, it attracts the springy metal. So maybe instead of using bounce the springy metal, okay, you turn clockwise, or maybe it's pulled to the right. So I would say it bounce the springy metal would, okay, or move to the right. Okay, then after that, the circuit will be open and the current will stop flowing. Okay, if you look at the answer, you'll find that all the answers actually revolve around the keywords or the labeling that's given in the question. Okay, the labelings that's given in the question. Okay, so we will make use of the labeling. The labeling is like a clue for you. Well, a clue for us to actually tell us why it works. Okay, to tell us what are the things that we need to actually write on it. So when we talk about analyzing the circuit, it doesn't mean the marker actually expect us to like look at the circuit from scratch, learn it from scratch on the day of the exam. No, the marker actually give us some clue already. He actually give us some clue to tell us where to start. When you start, which of the component are we looking at? That's why the marker actually make an effort to actually label all the necessary parts. Okay, not for fun, okay? Not just they want to confuse you, okay? The labeling actually is a way of marker trying to tell the students, please look at the labeling, please look at the flow. Okay. Then after that, part B is a DC motor. Okay. Simple DC motor with a split ring. Okay, now the current, remember the positive terminal is here. Okay, positive terminal means the current is moving here, moving inwards. Okay, moving to the left, the current is coming out. Same thing is going here. Okay, so it will be going up. Let's say coil P and Q, the current will be going upwards. Okay, so the current will be here. It will be going behind. So for RS, the current will be flowing in this direction. After that, return to the circuit here. Okay, and similarly for current, if you go through the split ring, okay, the current will be inside here, going through AB, BC, CD, then out again. Okay, so this is the flow of the current. The green color will represent the flow of the current. Okay, on the diagram A, B, C, D, indicate the direction of the convection current that flows. Okay, I have done it here. I've done it. Okay, you can take a look. Okay, how do I know the current start from left? Okay, because why? Because the questions give you the hint already, the positive terminal. Okay, so this is what I mean by appreciating the question. Okay, the marker does give enough clue in the question. Okay, so it's our job as students to pick up the clue. Okay, so please be careful, be alert. On solenoid RS, indicate the direction of the convection current, or I've done that also. Okay, a force act on arm CD. Okay, label the force, draw arrow direction of the force. What force are we looking at? CD. Okay, CD, we are looking at this branch. Okay, you have a current flowing in the magnetic field. How do we know it's a magnetic field? Because there is an electromagnet here. There's an electromagnet. The current is going upwards. Okay, if you use a Maxwell right-hand grip rule, you'll find that this is actually North Pole. This is actually South Pole. Same thing for RS. Okay, it's become a wrong color. For RS, okay, it become when the current flow through, okay, it become an electromagnet. Same thing if you look at the Maxwell right-hand grip rule, okay, you'll find that this particular R will be North Pole, S will be South Pole. Okay, so you effectively have a magnetic field line that is pointing from north to south, or what we call from pointing from right to left. Okay, so if you use, I have a field line. So at CD, the current is moving downwards. CD, the magnetic field line is going from right to left. Okay, so if you apply your Fleming left-hand rule, okay, left-hand rule, current and field lines, okay, your force field current, okay, so this will be your middle finger. Field line will be your index finger. Okay, if you use a Fleming left-hand rule, you'll find that your force will actually be pushing it downwards. Okay, so the force that is acting on the object here, so let me erase a bit so it's not so confusing. So the force acting on CD will actually be downwards. If you look at your Fleming left-hand rule, the induced force will actually be pushing downwards. Okay, and it will actually rotate the coil, okay, clockwise. Okay, so that's how I get the coil to be in the clockwise direction. Okay, so take note of this induced force. Okay, so you find that, let's say if you apply your Fleming left-hand rule here, on the coil CD, you'll find that the force will actually be pointing downwards. What force am I looking at? The induced force. Okay, so if you have a problem looking at the induced force, okay, you can look at my video at chapter 21 or 20, if you know, on Fleming left-hand rule. Now, same thing, what are the impact, how to affect the moment if the hollow paper clip is to replace with a soft iron core? Remember, soft iron core is to actually concentrate the field lines. The idea of using a soft iron core is to actually concentrate the field lines, aka, what does it mean? It actually, when field lines are getting closer to each other, they actually strengthen the field line. The field line actually becomes stronger, and because the field line becomes stronger, the force induced actually is larger now. So I will be able to rotate the thing faster. So as a result, I will be able to rotate the coil will be able to rotate faster. Okay, so take note of the answer. Excuse me. Now, question 9 is a refraction question. Okay. Now, the refracting index of the glass is 1.5. Okay. Now, same thing here. Remember, we are looking at section B now. Question 8, 9, 10 are section B. So section B, I will require you to choose 2 questions here. Okay, so and choose any 2 questions. Remember, don't just do the first question or just the last question. Remember to read through all the questions first. Then after that, choose the best 2 questions that you can do. Okay. Now, state why the light ray doesn't bend. Okay, I would say it's fairly straightforward. For light ray, remember, light ray, angle in the light ray, always remember angle pertaining to light ray, the angle incident or angle reflected. Okay, it's always from where? It's always measured from normal to the ray. Okay, so this you have to be careful. So when we look at angle, light rays, when we look at light, when we look at refraction angle is always measured from the normal to the ray itself. So effectively, although we say that the ray enter AC, surface AC 90 degree, okay, but the angle of incidence we are referring to here is actually angle 0 degree. Okay, and when we have 0 degree, okay, angle of incidence is 0 degree, okay, the angle will not bend at all. Okay, so take note of the instances. Determine the angle of incidence at point G. Okay, point G, where is G? Okay, point G is here. Angle of incidence, I'm looking at angle of incidence. So before I find angle of incidence, I need to know where is the angle of incidence first. The normal is here. Remember, it's from the normal to the ray. So this is the angle of incidence I'm looking for, angle I. Okay, so what is the angle I'm looking for? If you look at it, okay, you'll find that this is actually two parallel lines. So you'll find that this angle is actually 50 degree. Okay, corresponding angle 50 degree. If this is 50 degree, I will know that this angle here, it will be 40 degree. Okay, because both of them make up 90 degree. So straight away, I know angle of incidence will be 90 degree. Angle of refraction at point G. Where is G? G is here, okay? So my angle of refraction is 40 degree. Angle of refraction here is in the glass, in light ray, in the glass ray. So this angle I, okay, this is the angle in the glass medium, which is 40 degree. Okay, so refracting index, remember the formula? Refracting index is actually sine angle in the less dense medium divided by angle in the dense medium. In this case, the dense medium is glass. Okay, this is the 40 degree. This is in glass. So your dense medium, this is 40 degree. Okay, don't mix up the angle. I remember refracting index, the formula, the denominator has to be always in the denser medium. Okay, so that's why the 40 degrees here. Okay, 1.5 given in the question. Okay, so if you rearrange the algebra, the equation, you will get angle. Your refracted angle will be 74.6 degree. Okay, so it will be 74.6 degree. It will be a very steep ray. It will be somewhere here. Okay, so it will be 74.6 degree. Okay, arrow here. Okay, angle of incidence. Remember, it's always from the normal to the refracted ray. Now, same thing. If I change the glass block now, okay, you're going to change glass block. If I change the light ray now, you enter the glass block at at BC. Same glass block. So the refracting index is actually same 1.5. Okay. Calculate the critical angle of the glass block. Okay, straightforward. Critical angle is sine 90. Critical angle refer to where? The sine angle in the less dense. Critical angle means the angle in the less dense medium is 90 degree. Okay, so the formula will be here and you get answer straight away, 41.8. Now, angle of incidence at point H. Okay, H, angle of incidence, same thing as before. I need the normal first. I want the angle here. So this is the angle I'm looking for. Okay, so if you look at the angle here, it will be, let's say this is 50, angle in a triangle. Angle in this triangle here is 180 degree. So I will know that this angle will be 40 degree. This is 90. So if I know that is 90 degree, I will know that this angle will be 50 degree. Okay, simple geometry. Okay, so I'll get the answer 50 degree. Now explain whether subsequent path as it emerged into the air. Now, here, remember, take note of the critical angle is 41.8. The angle of incidence I have is 50 degree. Okay, now, here is because why? My angle at 50 degree is definitely much, okay, bigger. Okay, describe the subsequent path until it emerged into the air. So what happened now is the moment I hit surface H, okay, at H, unlike the previous question whereby the ray exit from the ray at 74.6, at this instance here, this light ray at H, it will not exit one. It will not exit. In fact, it will actually rebound. It will actually be reflected. Okay, at this angle. Okay, it will be reflected. Okay, and the angle will also be 50 degree. Okay, it will also be 50 degrees. Why? Because at this angle BC, okay, there is a total internal reflection. Okay, why? Because at angle 50 degrees, this angle is bigger than my critical angle, which is 41.8. So if I'm bigger than 41.8, my total internal reflection will occur. Okay, so I will end up at this particular location here. Let me erase it. So this is 50 degrees. So it will be reflected at surface AC. Okay, so now at surface AC, so what do I do? Okay, at surface AC now, okay, if you look at the angle at surface AC, the normal is at this area here. This is the normal at this angle here. So the angle I at this surface, at angle surface AC, okay, this is the angle I'm referring to. And now at this new angle, okay, this angle, even without doing any calculation, I will know that this angle, okay, angle I is definitely less than critical angle, which is 41.8. Okay, and what happened as a result? Okay, because it's less than critical angle, it will definitely emerge from the glass. Okay, it will emerge actually from the glass, okay, refracted away from the normal and out of the glass block. Okay, so you what I call it bend away, exiting the surfaces. Okay, so in this particular question, part 3, it's a 4-mark question. It actually requires students to do actually what we call in-depth analysis of the refraction or reflection at 2 surfaces. So the in-depth analysis, okay, will require the first 2 marks will actually give for the surfaces at AB, what happened. After that, the second 2 marks will actually go for the analysis at surface AC, what happened at the second point of incident. Okay, so that's what we mean by 2 marks question. So these 2 marks actually quite demanding. Okay, you require the student to actually look at the 2 surfaces. Okay, to put in critical angle or total internal reflection together with the standard refraction question. Question 10. Okay, question 10. Okay, the last question here. This question, if I'm not wrong, is about energy. Okay, conservation of energy. Okay, but Nathan, okay, climbing up the stairs, after that jumping from the springboard, which is, I think, for diving. Yes, it's for diving. Okay. Okay, the board is 10 meters above ground. Okay. Then after that, he climbs with horizontal constant speed. After that, he reached the springboard in 20 seconds. Okay. Mass is 62 kg. Okay. So 10 meters here. So let's see where we are. Okay, transformation of energy. As Nathan climbs from the ground to the springboard, I would say it's quite straightforward. Okay, from all my energy, all my muscles, I will convert from chemical potential energy. Oh, sorry. Oh. Okay, from chemical potential energy all the way up to the ground, all the way up to the springboard. Okay, so up to the springboard, it will definitely be gravitational potential energy. Okay, so how do I know is chemical potential? Because the question says when Nathan. Okay, so it's about Nathan's from the beginning, is from his body, from his stomach, what are the energy coming from. Okay, so that's where the chemical potential energy, after that all the way up to the top, which is gravitational potential energy. Average power during the climb. Okay, average power during the climb, power here refer to where? Power here refer to energy divided by time. Okay, so energy divided by time, the most straightforward way is to actually calculate the energy I have at part B. Okay, so the energy that we're looking at is when he reaches to the top. Okay, so to the top, we will be looking at the potential energy, which is MGH. Okay, so at the top here, the energy possessed here will be what we call the potential energy, which is the MGH. And he took 20 seconds. So the energy we're looking at MGH, which is 6,200, then divided by 20 seconds, you have the power, okay, of during the climb, okay, which is 310 watts. Now, based on the question is that Nathan, now he stepped on the springboard. Okay, oops. Okay, he stepped on the springboard. Okay, after that, to propel himself to a maximum height of 30 meters. So there's a maximum height. Remember, maximum height, like I mentioned before in the last paper, maximum height you also refer to whereby the speed actually is 0 meters per second. Okay, 0 meters. Okay, before he plunged, okay, Nathan pushes the board vertically downwards by 30 cm. Okay, and in return, the springboard returned to its original position. He propelled Nathan up, okay, upwards at a certain speed. So when the board returned back to the original position, Nathan is being pushed up, okay, at a certain speed. Okay, what's the energy gain as he leaves the springboards? Okay, now energy gain, he leaves from the springboard and reaches the maximum height. So what happened is at the junction here, let's say at the beginning here, he will definitely have a kinetic energy. So what it does is that at this point, this kinetic energy come from where? It comes from the elastic potential energy by the springboard. Now, what happened is this elastic potential energy, okay, is converted to the kinetic energy. Okay, this elastic potential energy is converted to the kinetic energy of the person. And after that, what happened is when Nathan is to the top, okay, is being converted to the potential energy at the top side here. Okay, so energy actually convert through different form. Okay, so it convert from the kinetic energy to the potential energy at the top. So if you look at the transformation here, is that from the elastic potential energy from the board, the energy is converted to the kinetic energy of Nathan at the when he leaves the board, when it's being propelled upwards, and eventually this kinetic energy is converted to the potential energy at the highest location. So if I want to calculate the energy that I have when it's leave the springboard, which is the energy of kinetic energy at point 2. Okay, if I can't find it directly, I can actually look at other versions. So example, if I want kinetic energy at point 2, position 2, I can actually look for elastic potential energy at position 1, or I can look for the gravitational potential energy at position 3. And these two positions, number 3 will be the easiest. So at position 3, okay, I'll have the potential energy, which is 6 times 10 times the 3 meter. Remember, okay, why not 13 meter? Okay, 13 meter is actually at the beginning here. Okay, at the beginning, this is a 10 meter. At the 10 meter, that 10 meter, okay, Nathan potential energy is there because of the location. He just climbed up there only. So where does the elastic potential energy here? What does this elastic potential energy from the board? This energy converted to kinetic energy and he propelled the Nathan up. This energy is allows Nathan to be propelled upwards by additional 3 meter. Okay, so additional 3 meter. And this additional 3 meter is what is needed, or what is needed for Nathan to reach the highest position, which is the potential energy at the 11 and 12, 13 meter. Okay, the top 3 meter here. So that's why the potential energy gain from the elastic board allow Nathan to go up by another 3 meter, which is why the potential energy at this location here is actually mgh, but the h is 3 meter, not 13. So take note of the conversion. Okay, because it allows Nathan to go up by another 3 meter. Calculate the vertical speed. Okay, so like I mentioned before, the potential energy is converted. The potential energy at the top come from where? It's converted from the kinetic energy at the boards. This is what we mean by position 3 and position 2. Okay, and same thing, energy is conserved. So kinetic energy is equal to the potential energy, which is half mv squared equal to 1,860 joules. You use algebra, you look at the answer to be 7.75 meter per second. Okay, work done by the springboard, same thing. So now springboard, this is the work done, which is the position 1. Okay, so the position 1, I repeat again, is here, position 1, the springboard. Okay, so position 1, okay, this is energy here. This 1,800 is actually position 3. Potential energy at 3, okay. Kinetic energy at 2. The elastic potential energy at 1. Okay, all these are conservation energy. All the energy actually are converted from one form to another form. Okay, all of them are, in this case, the ideal, all of them are 100% converted. So the energy will actually be converted from 1, 2 to 3. So that's why I can safely say that the elastic potential energy at position 1 is actually equal to the potential energy at 3, which is 1860. Okay, this is your 1860 joules. Okay, and the elastic potential energy at potential energy at position 1 is what we call the work done. Okay, so that's why these two are equal, which is where I derive this formula here. Okay, so given that the object work done, the distance moved is 30 cm. Remember, this is 30 cm. Okay, convert to meter, it will be 0.3 meter. SI unit, SI unit. Okay, and the force, okay, exerted by the springboard, okay, will be 6,200 Newton. This is the force that allows Nathan to be shoot up, okay, for another additional 3 meter. Okay, and after that, okay, with this, okay, this will be the last question. This will be the last question for this particular paper. Okay, overall, this paper, take note, okay, there are some important things, some small, some, I will not say small, I will say there are some aspect of the topics or the questions that we actually never really pay much attention to. And that's the beauty of this paper. We actually touch on this area that we tend to miss. Okay? If we never practice this paper, we will tend to miss out this area, and it may actually result in some questions that we might not able to do on the day of the exam itself. Okay, so the important thing for exam paper is actually to look at the gaps that you are you have, and after that start working on it. Okay, and how do we know the gaps that we have is by through practicing. Okay, look at how you solve the questions and what are the thinking process that's involved in solving the question. Yeah, and from there you'll know that what are the gaps that you have in your thinking, in your working, in your ideas, and in your revision. And after that, okay, bridge the gap. Okay, patch up the gaps. Okay, touch on your key characteristics, or maybe some of the missing area or this thing. And after that, practice again. Okay, important thing about physics at I would say at this level is about consistent work. Okay, it to be consistent in your reading, your revision, and even in your practicing. Okay, to have a systematic approach towards learning. Okay, if not, okay, this is where I end off in my paper here. Okay, remember, if you need a paper, it's in the description bar below. Okay, and if you need anything, just give me a comments at the give me an email, or write your comments in the comment bar below. Okay, if anything, okay, I will be uploading a few more papers. Okay, remember to subscribe to my channel. Okay, if you want to get the latest update, okay, remember to switch on the bell also. Okay, so that you get any notification whenever I upload any interesting video that might be useful to you in the future. Okay, if not, see you.